Welcome students, we got an interesting question. We expected to integrate integral x raised to the power of x times dx. Now foremost I would like to rewrite x raised to the power of x to be as with some base. I'm going to use e. So e raised to the power of ln x raised to the power of x. The base is e, so this is nothing but the left hand side. So this would mean integral x raised to the power of x is going to be e raised to the power of ln x raised to the power of x times the dx. Now from logarithm, ln a raised to the power of b is equal to b times ln a. By that formula, this is going to be integral e raised to the power of x times ln x times dx. Now I know that e raised to the power of x is 1 positive x over 1 factorial, positive x squared over 2 factorial, positive x to the power of 3 over 3 factorial plus etc. Which is nothing but sigma n is equal to 0 to infinity x raised to the power of n divided by n factorial. So therefore e raised to the power of x times ln x can be rewritten using this series expansion as sigma 0 to infinity x times ln x raised to the power of n divided by n factorial. Now this can be rewritten as n is equal to 0 to infinity x raised to the power of n times ln x raised to the power of n divided by n factorial. So in place of this I will be utilizing this. So if I were to take this as 1, therefore I can rewrite 1 to be as integral sigma 0 to infinity x raised to the power of n times ln x raised to the power of n divided by n factorial. This can be rewritten by taking sigma out, 0 to infinity 1 over n factorial integral x raised to the power of n times ln x raised to the power of n. Now of course you have the dx there, we need to place the dx. Now I will like to make the following substitution. Let ln x be equal to some u. This has got a base e, so this means e raised to the power of u is equal to x. So if I were to differentiate this, I can actually get dx. So let me get the dx over here. So if I were to differentiate both sides, I get 1 over x times dx is equal to du. Fair enough, we need only dx, so push this x to the other side. Therefore dx is equal to x times du. But what is my x? X is e raised to the power of u times du. Now if I were to take this as 2, therefore I can rewrite 2 as sigma 0 to infinity 1 over n factorial integral. In place of x I substitute e raised to the power of u. This has got exponent n, so this will become n times u. And in place of ln x I will be substituting u, so this is u raised to the power of n. In place of dx I will be substituting e raised to the power of u times du. Now these two can be clubbed, so that is going to be sigma 0 to infinity 1 over n factorial integral e raised to the power of, now u can be taken out, so that's going to give me n positive 1 times u raised to the power of n times du. Right? Now we need to integrate this, so I want to go to the next slide. So this is equal to, what I wish to do is I would like to substitute let e raised to the power of u times n positive 1 be equal to some p. Okay, so I take ln both sides, so ln e raised to the power of u times n positive 1 is equal to ln p. Now ln e to the base e, so that would mean you have u times n positive 1 is equal to ln p. Now you differentiate u, you get du. This is going to be constant, n positive 1 times du is equal to 1 over p times dp. So this is what you have got. So du is equal to 1 over p times of n positive 1 times dp. So what is the integral given? This is the integral given. Let me write that down. So if I were to take this as 3, okay, so I will rewrite it. So therefore 3 can be rewritten as sigma 0 to infinity 1 over n factorial integral e raised to the power of u times n positive 1 times u raised to the power of n times du. This is rewritten as sigma 0 to infinity 1 over n factorial integral. As I mentioned to you, this is taken to be as p, it's the substitution, so it's going to be p there. And u raised to the power of n, u, we need to get the value of u. So from here I would extract the value of u. So u is equal to 1 over n positive 1 times ln p. So take the value of u and substitute it here. So this is going to be ln p divided by n positive 1, and this is raised to the power of n times du. So what is my du? My du is this value. So we need to have that value there. So it's going to be 1 over p times n positive 1 times dp. Okay, fair enough. Now clearly you have a p here, you have a p here, so they get cancelled. So rewriting this, sigma 0 to infinity 1 over n factorial. Now I want to split this. So this is ln p raised to the power of n, fair enough. And then you have n positive 1 raised to the power of n, and then you have n positive 1 times dp. This is what you have got. Okay, now these two can be clubbed together. So that would give me 0 to infinity 1 over n factorial times n positive 1 raised to the power of n positive 1. Okay, followed by integral ln p raised to the power of n times dp. So we need to make a substitution to handle this. Okay, so let's do that. So let me take ln p is equal to some t. So this would mean p is equal to e raised to the power of t. Now let me differentiate this. This would give me 1 over p times dp is equal to dt. So I need to get dp. So therefore dp is equal to p times dt, but my p is this, so it's going to be e raised to the power of t dt. Fair enough. So if I were to take this as some 4, therefore 4 can be rewritten as sigma 0 to infinity 1 over n factorial times n positive 1 raised to the power of n positive 1 times the integral ln p is t raised to the power of n, and then dp is e raised to the power of t times dt. Okay, fair enough. Okay, now what I wish to do is I would like to apply the series expansion for e power x again. Now e power x is nothing but sigma 0 to infinity x raised to the power of n divided by n factorial. Now I don't want to utilize n again because n is already present, so therefore I'm going to utilize e power t to be equal to some sigma, say s is equal to 0 to infinity, right? And you have t there, so t raised to the power of some s divided by s factorial. Now I need to place this quantity n there, so in place of n is going to be s factorial. Now we are not utilizing x, we are utilizing t because of the fact we got e raised to the power of t. Okay, fair enough. So s is ranging from 0 to infinity. Now I would like to replace that value over here. Okay, so let me go back, let me go to the new page. So this is equal to, let me keep that in the frame, this is equal to sigma 0 to infinity 1 over n factorial times n positive 1 raised to the power of n positive 1 integral. Now t raised to the power of n, that is retained as it is, no harm done to that, and then e raised to the power of t, that is going to be sigma, as I told you, I've taken the index variable as s is equal to 0 to infinity and t raised to the power of s divided by s factorial. Okay, it's a factorial there, times dt. Okay, so now you can take that sigma out. So this is one sigma is going to be 0 to infinity of 1 over n factorial times n positive 1 raised to the power of n positive 1. The another sigma is actually s is equal to 0 to infinity and 1 over s factorial followed by integral t raised to the power of n times t raised to the power of s times dt. Right, now s and t are actually values that are basically, they are all parameters, right, index parameters that are actually moving from 0 to infinity. So I can treat them as a constant, right, with reference to the variable t. Now what I'm going to do is I'm going to club these two together, so the sigma together, I'm going to write it as sigma 0 to infinity for the first quantity followed by the next sigma. Let me just specify it, n is equal to 0 to infinity, and I will just substitute s factorial there. Okay, times integral t raised to the power of n and s, so I can add them like that, right, into dt. Now as I just given you that explanation, this can be rewritten as n is equal to 0 to infinity and then s is equal to 0 to infinity of 1 over n factorial times s factorial times n positive 1 raised to the power of n positive 1. If you were to integrate this, this is going to give you t raised to the power of n positive s positive 1, okay, divided by n positive s positive 1. This is what we will get, okay. But we made a substitution, okay. Now what is the substitution did we make? We will have to revert that back, okay. But we made the substitution. What is the substitution we made? We took t to be equal to ln p, so you revert that back, but the value of t is equal to ln p, right? So this is equal to sigma n is equal to 0 to infinity, sigma s is equal to 0 to infinity, 1 over n factorial s factorial times n positive 1 raised to the power of n positive 1 multiplied with ln p raised to the power of n positive s positive 1 divided by n positive s positive 1, okay. Now this is an indefinite integral, so you have to place that arbitrary constant c.